So we already saw what is a scanning tunneling microscope and what are the features of it. Okay, but it had a problem, right? What was the problem? The problem was that only conducting sample, okay, at least very small samples or conducting samples were the only possibility there. And most of our materials are non-conducting. Okay, a majority of our samples are non-conducting. So STM is not of use there. That's why they again thought that, okay, I mean the same group in IBM, okay, they thought that, I mean, there should be another way of picking up atomic resolution, okay, using a different mode. So if you want to capture electron, the material has to be conducting naturally. So if it is not a conducting material, what can we do? We saw before, we can capture the force between something, okay, force between a surface and maybe a probe, different type of probe, which is not a conducting probe. That is where atomic force microscope comes. Okay, so AFM again was discovered by the same group, but different three people. One Binning is there, and Quaid and Gerber in 1986. You see, soon after their first Nobel Prize, they developed this one. Okay, so the technique is very simple. Okay, so in STM we captured the electrons from the last orbital and we mapped atoms. Here what we are going to do is that we have a very sharp tip again, and when there is no voltage applied, no current, no electricity is required, but at least no voltage there. Okay, so the tip comes very close to the surface. Now what happens when the tip, there is a last atom of the tip, there are atoms on the surface, and when they come closer there is van der Waals interaction, right? What is van der Waals interaction? I'll tell you in the next slide. So the tip, initially the first generation of AFM was not just a van der Waals interaction, but it was actually scanning on the surface. Okay, so it is like a very sharp tip. We have a surface and it is actually scanning, rubbing on the surface. Okay, it is actually moving on the surface. Then you can actually see the deflection. Okay, so if I have a cantilever like this and I have a tip here, and if this cantilever is moving on the tip, so basically it will jump over. Okay, like our some bumps in the northern sides we can see Kerala, right? Lot of bumps successively, and our vehicle will jump like anything. So like that here. So now the thing is that the tip is going to jump, and we have to capture that jump. Okay, what to do? There's a small laser, and this is like a mirror. Okay, so the laser is now reflecting back. This is a photodiode. Okay, so there's a photodiode like this, and naturally, if the tip is jumping, what happens? The diode deflection also will change. Okay. So knowing the deflection, this is a quadrant. I will show in the next slide. This is a quadrant photodiode. So knowing where it is moving in this direction or this direction here, where it is moving, I can actually see in which angle or in which mode this deflection happens. And the deflection is proportional to the spring constant of this cantilever. Okay, this is a cantilever. So basically, if this is going to deflect, the force is measured as kx. Okay, x is how much I am pulling. Okay, and this has a spring constant, so k into x minus kx, basically that is the force acting on it. So I can know if the tip is actually coming closer and closer and closer, and then if these surface atoms, if they are going to exert a force on the tip will deflect. Okay, and how much is that force I can exactly know if I know the spring constant of this cantilever. So if you look at the AFM cantilever, together with AFM there will be a set of cantilevers also. For every cantilever you can see what is the spring constant written on top of that. Okay, so that is required for calibration of AFM, because you want to know what is the force. Then only we can actually calibrate what is the force exerted there. So basically the deflection of this cantilever, and it can be because of the rubbing of the tip on the surface, or it can be away from the surface, but there is still something called van der Waals interaction. Okay, you will get deflection because the tip is now attracted by the surface. Okay, if there is some molecules there, that attraction again will be same sample distance, sample to tip distance is important here. Okay, because previously it was the tunneling distance, now this is the van der Waals interaction distance. Okay, why van der Waals interaction is important? Okay, this is like a blind, it's called blind technique, because we just feel it's like feeling the force and measuring what it is. Okay, very simply speaking, this is how van der Waals interaction comes. Suppose this is the tip and this is the sample. So when the tip atom and the sample atom come closer, we have this nucleus will attract the electron cloud of this atom, so it will elongate a little bit. So basically like a polarization. Okay, so positive charge attract this electron cloud, this positive charge attract this electron cloud. There is a repulsion of this electron cloud and this electron cloud. There is a repulsion of this two nuclei. Okay, so opposite charges they attract and the similar charges repel. So what happens? Totally, the total force will be a combination of attractive forces and the repulsion. Okay, if you bring these two atoms closer and closer, the repulsion increases. Okay, because this electron cloud will repel this electron cloud, this nucleus will repel the other one. So more than, if it is far away, attraction prevails, and then if you bring these two atoms closer and closer, it becomes into attraction plus repulsion, and then repulsion increases, and then it becomes totally repulsive. Okay, so that total force, if you are plotting, this is the potential energy because of the attraction and repulsion. Okay, this is a Coulomb force basically, and this is the distance. What happened? You see, this dotted line is the attraction. Okay, attraction of this nucleus on this one, and this nucleus on this electron, and like that. Okay, so this is the total attraction, and repulsion of these charges. That is this line. Okay, if you add these two things, these two attraction and repulsion together, you will get the resultant line like this. And that's our famous van der Waals curve. Okay, which means that if I am standing, if the distance between atoms is somewhere here, I am still in the attractive regime. Okay, this is the potential minimum. So always these atoms prefer to come to this point and stay here. Okay, for example, if you take a molecule, sodium chloride, there is a distance between sodium and chloride. Why? Because when they come closer and closer, wherever this distance is coming, that is the bond length. Okay. And if you try to squeeze them, it goes to repulsive mode. If you try to take away them, it will go to the attractive mode. Both are not balanced. So this is the distance at which the forces are balanced. So you get that particular distance as the bond length. Okay, and there are more things to it, but simply speaking, okay, from the perspective of van der Waals forces. So this is the basic diagram of an atomic force microscope. Now, what are these? So this is the sample atoms, and this is the tip or the cantilever. At the end of the cantilever, there is a tip, and the end of the tip there are atoms, few atoms. So basically, this curve we can actually plot if you have an AFM. Okay, you just measure the force and measure the just like a tunneling current we measured. Okay, as a function of distance, you measure the force here. You will get first this curve, van der Waals curve. Then you know that okay, this is the equilibrium position where we can define that the sample is, or the tip is touching the sample. Okay, and if you are pressing, you are in the repulsive mode. If you are taking out, you are in the attractive mode. So when exactly it is touching, that is our equilibrium distance here. Okay, so basically using a tip and sample, we can you can just put the tip closer and closer to the sample, and you just take it away. You will get this curve. Okay, if you keep on pressing, you can actually trace the entire curve. During my PhD, I had to develop a AFM. Okay, actually I will show you, that is called the friction force microscope. So the first thing to know whether our AFM is working or not, after making it, we make a van der Waals curve. Okay, so bring the tip closer, and then we know that just like we are in the tunneling regime of STM, we will be in the scanning regime of the forces. Okay, so this is the equilibrium force where the tip is just touching the sample, and then if you scan over the surface, we can get a very good resolution. Okay, just like a STM. So there we were in STM, we were measuring the tunneling current. Every pixel was tunneling current, and here what will be the probing? Basically what happens is that, you see, the laser is reflecting here. This is a photodiode. Okay, every deflection will give you a photocurrent, and that photocurrent again we are giving back to the feedback. The rest of the electronics is the same. Okay, just like feedback will tell if the photocurrent is larger, that means deflection is larger. That means we are very close to the surface. And if you want to reduce that one, feedback will come. It will take away the tip. Okay, and normally for understanding, it is easier to say that the tip is scanning over the surface. But if the tip is scanning over the surface, this is a cantilever, if it is moving, what will happen? It will be keep on vibrating. Okay. So for easiness or for the benefit of the measurement, we keep the tip constant, okay, or the cantilever constant, and measure the surface. Okay. The surface will be moving. That is more practical. Otherwise, there will be a lot of noise. Okay. So the surface will be. So that's why this piezo scanner, okay, piezo tube scanner is here. So that the surface will be moving here and here in 2 dimension, and the tip will be a constant. But the deflection of the tip we can measure by this for the quadrant photo detector there. All these things are already set in a AFM. You don't have to do any of these things. Okay, but just starting from beginning. Okay. Now, if there are again different modes of scanning. Okay, here we are measuring force. The force will be larger if the tip is really touching the sample. Okay, because according to that curve, if the tip is touching the sample, the force is maximum. Okay, and we can actually increase the force, but then we will be in the repulsive mode that will damage the tip. Okay, because we are pressing on the sample. So we need to first of all, this is called contact mode. Okay, contact mode means we are actually coming down and touching the sample, and we know that the sample is on contact with the surface. Then we are slowly, very softly patting on the surface basically, right, with the tip. And then we know what are the surface features, and every pixel we can see, because every pixel gives every deflection gives you a pixel, so we can map it and then we can do it. Okay, but there is a problem with the contact mode. Contact mode means when the tip comes closer and closer, you see we are in that attractive regime. Now what happens? The tip will jump into contact. Okay, this is the jump. Okay, so it will jump into contact because you see, look at here, the tip is coming closer and closer, and it's like an attractive regime. So this attraction increases here. The tip will electrostatically jump into the contact. And once it jumps into the contact, it is not easy to pull it back, because now it is like a glue. Okay, it is now glued there, because now the atoms and the surface atoms are in contact. There can be water in between. There can be anything in between. It's like a paste. It will just stick there, and then we need to exert larger force to take it out. That's why you see when it goes into contact, it jumps into contact, and basically the same figure, but this is the practical one. And you see, if you want to take out the tip from the surface, you need to exert a larger force, and most of the time that kills the tip. Okay, because the cantilever can break, because it is coming and it goes like this. Okay, so there can be damage to the cantilever if you are doing that one. Okay, so this one. So contact mode is very good for getting very high resolution, because you are directly contacting its maximum force you are getting from the sample. But that can do two things. One is snap. This is called snap into contact, jumping into contact. Second problem is that if the sample is very soft, like a biological sample, okay, you can basically destroy the sample, because you are actually moving on top of the sample. Okay, so you will get the best resolution if it is in contact mode, but for soft samples it is not recommended. Okay, so keep that in mind. So this is van der Waals forces in nature. Basically, this is how a lizard is hanging from a roof. If you look at the hands of the feet of the lizard, okay, in a microscope you can actually see millions of or thousands of small what's called fur which is coming out. That's called lamella. Okay, and they have van der Waals force. Okay, the van der Waals force between these small fur or hair like things and the surface is the reason why it sticks there. Okay, and the important thing about van der Waals force is that, again, snap into contact. Remember this one. If you just want to take out like this, you have to exert a very large force. So lizards when they are walking, if you just very carefully looking, they are not taking hands like this. Okay, they are taking like this, like our strips on the shoes, right? So we cannot just pull it like perpendicularly. We have to strip it like this. Okay, because we have to remove that contacts one by one. Then it is easy. So if you understand that, right? That strip. So if you just paste that strip, you just try to pull it perpendicularly. It's very difficult. But you can open it like this, okay, by tearing it. Like that, the lizard is actually moving. Okay, they cannot just take it like that perpendicularly. They have to tear it and go like that. Okay, and this has brought a lot of different type of machines. Okay, it can actually jump. This is an artificial lizard. Okay, for students. And this guy is actually hanging on an artificial limb of the lizard. Okay, so he has made, at the end of this thing, there are a lot of small nano wires hanging, and we can actually hang it. And if you just want to move like that, he will not fall down. Okay, so because you need a large force to bring it back. But you can actually tear it and put it there, tear it, put it there, like that he can actually move. Okay, exactly like a lizard. This is the basics of AFM, and this is the problem with the contact mode. We cannot tear the tip like this in the AFM. So snap into contact means you need large force to release the tip. Okay. Yeah, so this is how the tip is. The cantilever is usually made of silicon, because silicon etching and silicon fabrication is a standard process. So you can very easily make silicon tips. And these all are etched in silicon itself. Okay. Sometimes it is coated with the silicon nitride, because silicon nitride is a hard material. Okay. Otherwise, what happens here? Our scanning is with the contact mode. If you do the contact mode, the last atoms can actually, finally what can happen? It can tear off atoms from here. The tip will be blunt. Okay. To avoid that, you can actually coat with hard materials like silicon nitride, and then mostly these are silicon nitride tips, coated tips. The silicon tips, but silicon nitride coated. And silicon has one more advantage. We know everything about silicon, because all our CMOS technology is silicon. So if you make a cantilever like this, just looking at the geometry itself, we can predict what will be the spring constant. Okay, the force constant, what will be, that we can already predict. So we don't have to really measure it. By the etching itself, we can actually see what is the spring constant. There are different types of springs available. For example, this is another cantilever like a shape. Okay, so this shape also is available. That depends upon how much stiffness you need. Okay, and how much flexibility you need. For different samples and different type of AFMs, you need different type of tips and cantilevers. Okay, so that's why different geometries. Normal cantilever is like this. Okay, these two are the normal cantilever. So the cantilever is fixed there. This is the sample, and there's a small laser. You can actually see a red laser coming in when you open the AFM, right? I hope you are going to see that maybe in the afternoon or so. So you can actually see a laser coming. This is going to this is called a quadrant photo detector. So this is divided into 4. And the first thing is that we have to nullify the signal. Okay, which means that already the signal should not be in any of this quadrant. It should be in the middle. So that's a 0 signal. Okay, and from there we have to, if you do the deflection, we can see which direction the deflection is happening. And this geometry also is special. This geometry doesn't allow it to wobble like this. Okay, it will be stiff. It can only move like this, because if the tip is here and while scanning, if it is wobbling like this, you see that signal will go all the way. Okay, to avoid that, that's why this special geometry is there. The thickness also is special. All these are using FemLab or simulation tools. It is already designed and fabricated. Okay, so it won't wobble like this. It will move only like this. Okay, it is very stiff in this direction. And if you want to avoid that, to increase that stiffness in other directions, you can actually use this geometry. This will not be wobbling again, but that is a more costly type of tips. Okay, cantilever. So this is our normal cantilever. Put it there. We can actually take a cantilever using a tweezer and put it there. Okay, you will get a set of cantilever with the AFM. You can buy it again. And then the first thing is actually to nullify this, to make it 0. The difference between any of these things. Okay, so if it is deflecting like this, we can actually see where it is deflecting, how much it is deflecting, all those things we know. The deflection is proportional to the force between the tip and the sample, right? So more deflection means larger force. So we know where it is coming, very close to the surface or away from the surface. Okay, so instead of the tunneling current, here we measure the van der Waals force basically. So this is the simple equation here, not like STM. So we have only this force constant of the cantilever. This is normally an AFM looks like. Okay, so it's you will see in the afternoon. Okay, so then all these things are basically electronic noise reduction. Okay, because there's a very easy way to reduce the vibration. So if it is standing on a magnet with springs or wire around, if any vibration comes, what happens? Eddy current will pass. So that eddy current will stop the vibration. Okay. So this is called eddy current stopping. This is electronic vibration isolation. Okay. Because any of these techniques we need to avoid vibrations. So to avoid vibrations, these are all for avoiding vibrations. These all checks, and again this will be standing on a optical table to avoid further vibration. In STM we put additional sponge on top to avoid any other vibration. Then also a cover will be there to avoid vibration because of our speaking or sound like that. Otherwise, if a bus goes through IAST, I can see all atoms. Okay, it's jumping like that. So we put the sample here. All the detection, it's very small actually, very small part. The sample holding detection, everything is here in a very small area. So again, this goes to the feedback, because this part is fixed. We cannot move that because it's a force constant, and cantilever means there is a vibration, so we have to avoid the vibration. So it will be moving, and we will get a topographical image or topological image like that. Okay, so it's very simple in that sense. So this is a graphene imaging. So what happens is that when you go from one layer to the other layer, it's around 3 angstrom step height is there that you can clearly measure using AFM. So the resolution limit of STM is picometers. Okay, that means 1 in 1000 of an angstrom. Okay, but nothing exists in that level. So that's only the pixel noise level. Okay, but here also that type of resolution you can get. You won't get, unlike STM we are measuring the electronic configuration, right? The last orbital electrons. But here that's not what we are measuring. We are measuring the forces. So basically, if you take a hexagonal carbon like a graphene or graphite, and using AFM, if you are measuring atomic resolution, you can actually measure the bond strength between carbon atoms. Okay, people have measured it. It's a paper in Nature came actually. So you can actually measure the bond strength. The bonding you can actually very clearly measure using AFM measurements. Okay, I think I have an image somewhere. So contact mode AFM may be problematic for soft samples. So if you have a rigid sample, contact mode AFM is good. If you have a very flat sample and you want to have atomic resolution, contact mode is the best. Okay, for atomic resolution, if you need that high resolution. But if it's a soft sample, contact mode will not be useful. Okay, will be damaging. That's why non-contact mode is there. Now you are not in contact, you are a little away from the surface, but still you can feel the van der Waals force. Okay, you are the attractive regime, but you are not touching it, you are a little far away from here. So for soft and biological samples, that is a good method. Here this is the problem. So if it is contacting, if it is touching, especially biological molecules, there will be OH groups. So that the tip also is hydrophilic, means they will attract each other, and you need to break that bond to get it out. Okay, so that's not good for the contact mode is not good. Okay, you have any question? No? Okay. Yeah. So this is the problem. Okay, capillary. This was my PhD topic actually. The capillary formation between the tip and the surface. Okay, it can even at a room temperature, if water molecules gets in between the tip and the surface, what happens is that will freeze there. It will form ice. Okay, even at a room temperature, because only a few monolayers of water is coming there, and we have tip here which takes the heat out. We have a sample here that also take heat out. The molecules will suddenly crystallize there, and if you want to move forward, we have to break this ice, and then moving forward, it will form again ice. Okay, and we could actually see lines of ice if that happens. So contact mode has that problem. This anything can get in between the tip and the sample. It can create ice, or no, it can create large force between the tip and the sample. In non-contact mode, the tip is oscillating. Okay, so it's not just going like that. The tip is slowly oscillating like this, and then what happens? That means it is coming closer and going away, coming closer, going away. Okay, so you are coming into the attractive regime, going away, and coming again, attractive regime, going away. What happens? The cantilever has a certain resonant frequency. Okay, because it's a cantilever. So if I just like a tuning fork, if I just press it, it will just vibrate. So it has a resonant frequency. Now that resonant frequency is because it is a free cantilever. Now suppose this cantilever comes closer to a surface. Now what happens? It is like I am attaching another spring here, which is the van der Waals force. Okay. Now if anything is vibrating and I am attaching a rubber band here, for example, that vibration will be damped. damping, right? And the amplitude of vibration will change, phase of the vibration will change, everything will change. Okay, the frequency also will slightly change. So if it is vibrating on top of a surface and not touching, okay, there's another mode coming which is tapping mode. I will tell you that later. So if it is vibrating, what happens that the vibration amplitude changes, the frequency shifts a little bit, and the phase also shifts a little bit. At the same time, you are going to get three images. Okay, one is the amplitude image, another is phase image, another is frequency image. Okay, and all these three will give you three different information about the same sample. So that's why AFM becomes more popular than STM. Okay, you can actually, STM gives only the surface, but AFM can also give you something, slightly inside the surface also you can get information. I will show you the details. Okay, so this is the resonant frequency of the cantilever. This also we can actually see, probably in the software you might see this resonant frequency. Okay, that is when you put a new cantilever, you will see the resonant frequency, where the resonant frequency is. And you take it at the 0. Okay, for example, you put it at F0. That's the fundamental frequency of the vibration of the cantilever. Now, when the tip comes closer, it's vibrating and coming closer, what happens? It will shift a little bit. Okay, so that shifting is because there is an additional force here. Okay, again remember, a tuning fork which is vibrating, if you are attaching a rubber band there, it will be damped. Okay, all this phase, amplitude, everything will change, and there is a slight change in the frequency also. So frequency shift, amplitude shift, all these things at the same time from the same sample. Okay, so you will get three different ideas about that. I will tell you what all you can measure. So this is about frequency modulation, non-contact mode. First one was contact mode. There the tip is not vibrating; it is just dragging on the surface. Okay. Good for very flat samples to get very good resolution, but for soft samples and very soft tip, it is a problem. Okay, so tip will get damaged because you are rubbing on the tip on the surface all the time. Here, it is away from the surface. So what happens? Naturally, the resolution goes down. Okay, because you are far away from the surface, the force you are going to measure is smaller. So the resolution will be bad compared to contact mode. Since its force is equally better, it's not direct contact with the surface. Okay, equally better means still the resolution will be bad comparing to contact mode. So atomic resolution usually is done with contact mode. Okay. Yeah. So this is what I was saying. So this is the tip spring, and this is the van der Waals force, which is equivalent to a spring. Okay. So this is the van der Waals force, which is equal to a spring. So totally the vibrational amplitude and phase and frequency will be changing. So this is a two spring system now. Okay, this is the cantilever spring and this is the van der Waals force. So van der Waals forces, the dipole interaction can be there because if there is a polarization of the tip with respect to sample, that force also will add up. It is not only just a van der Waals interaction, dipoles. Now you will see there is something called magnetic AFM is there. Kelvin probe AFM is there. All these things are using, basically everything is same diagram, only this spring is going to change. Okay, in magnetic AFM, the tip will be magnetic, sample also will be magnetic. So we can actually measure the magnetic domains on a surface. Okay, so that's called magnetic AFM, we will come to that. So now, so this is contact AFM. Contact AFM is in this regime, from this regime onwards to the blue regime, there is the contact because we are pressing the sample and then dragging the tip on the surface. So we will be working in that regime. And non-contact AFM means we are actually away from the equilibrium position. We are not touching the sample, it's slightly above the sample. Okay, so that means there can be a regime where exactly in the middle. Okay, the middle means the tip is now going to snap, and then it will be difficult to get it back and it will be scratching on the surface. But we need high resolution at the same time. We should not damage the surface. Then what we should do? We should tap on the surface. Okay, so instead of dragging or instead of going away, intermittently if we are tapping on the surface, we can get high resolution because we are touching the surface and immediately we are coming back. Before snapping into contact, we are taking it back. So just like tapping on the surface, we can get high resolution. Okay, and that will not damage the sample because we are not going to this high force here. We are not going to press the tip on the sample. Okay, so that's basically called Okay, this is contact and non-contact modes. Again, like I said in the STM case, constant current and constant height mode. Here also constant force mode and constant height mode is there. Okay, so constant height mode, again, height will be constant, force will be varying. That height constant is given by the feedback loop. Okay, and the force is measured in the second one. Okay, so here constant height and constant force mode. Both we can use depending upon the flatness of the sample. Basically, there also you have to be careful. If very rough sample, height has to be constant. Okay, then feedback takes the voltage given to the piezo of the surface, and then you can map the surface. Okay. This is the tapping mode. Okay, so this is what we generally use nowadays. Tapping mode is more famous or more useful. Okay, so tapping means it's again oscillating with its vibrational, it's the natural frequency of vibration, but it's actually now it's not vibration oscillating above the sample. It's actually tapping. That means it's coming in contact once in a while. Okay, not once in a while. Every tapping it comes into contact with the sample. Then what happens? If you give enough time, it will snap into contact. Before that, you are taking out. Okay, so the tip taps on the surface intermittently. It's a mode in between the contact and non-contact mode. So this is good for all type of samples, biological samples and soft or hard samples. Okay, so tapping mode overcomes major problems associated with the friction. There can be friction if the tip is on the surface. Basically, we cannot take it back. Means, and if you are scanning, we are having friction there, and that is called friction force microscope. That has several other advantages. Okay. So friction, adhesion, electrostatic forces between tip and sample, all these things can be avoided if you have intermediate tapping is there. Okay, so it is like that. So it is not away from the surface, it's actually tapping on the surface. So amplitude drastically get reduced. Okay, because now we are really tapping on the surface. It's not like away, like a spring. That spring will be hard. That van der Waals force spring will be very strong if it is coming very close to the surface. So tapping means amplitude reduction will be very large. There will be a very strong phase reduction also. Phase means what? We are actually giving a force on here, right, for tapping it. Now that has a particular frequency of vibration or oscillation. If the phase is changing, that means if it coming closer, that vibration will shift. Okay, and using a lock-in amplifier, we can actually compare between the natural vibration and the vibration after coming into contact, and that gives you the phase shift. Okay, so the frequency shift, amplitude shift, and phase shift also can be measured. Phase shift actually depends upon how hard the material is. Okay, that's another interesting thing. If it's a soft material, that's what I was saying. Comparing to STM, the difference in AFM is that it can actually measure something a little bit of inside the material also. So the tip comes here. It is not only just interacting with the last or the surface atoms. It can actually, if it is a fluffy sample, okay, the entire elastic properties can be measured here. Okay, so if it's a soft material, for example. And if you are, suppose the surrounding is a hard material, you have a soft material on top. If you are actually coming and contacting in intermittent contact with them, this contact, you see, it's just pressing it and coming away, right? So you can actually see the strength of this material or softness of the material also you can measure. Okay, I will show you some examples there and I will explain them there. Okay, so intermittently placing the tip in contact with the surface, that is what is tapping mode. Okay. So tapping mode is like that. So it actually comes into contact, goes away, comes into contact, goes away, like that. Okay, so it doesn't really snap into contact. It just taps and gets away. Yeah, you can see an example here. This is a DNA sample. Okay, this is a tapping mode. You see very good resolution we can get. At the same time, okay, this is a hepatitis B virus. Okay, these are all height images. You can actually see this is height. Height means you can actually see we are going like this, and whatever is the feedback coming, we can actually plot it. That will give you the height of the material. Okay, and amplitude. So height, amplitude, and phase image you can get at the same time here also. So phase image will tell you how soft that material is. Suppose you have a surface which you don't recognize whether it is soft or hard. It looks the same. Height is the same. If you look at the phase image, you can see that there's a difference between hard portion and the soft portion. I will show you an example. Okay, so this is again non-contact mode. And non-contact and tapping mode you can use intermittently to get a high resolution, okay, for both this information, because in both non-contact mode and tapping mode we are using the vibration of the tip, okay, the tip is vibrating. Contact mode there is no vibration, it's just dragging on the surface, but non-contact mode and tapping mode there's a vibration, so we will get amplitude, phase and the height images at the same time. So you see this is an AFM height image, so this is where this is a polymethyl PMMA, right? No, PMMA granules actually. So it's a soft material basically, and if you look at the this is the height image, at the same time we are getting the phase image also. So phase image you can see more details actually if you look very carefully, right? Some bubbles like things you can actually see. That actually is not visible here because this is a height image. We can only see a average of the image here. But here what you see is that there are molecular structures which are clubbed together. Okay, so one portion will be hard, one portion will be soft. So even the details of this structure we can recognize from phase images. So phase images can actually tell you, especially if it is a biological sample, phase images can tell you really about what is inside. Okay, this is an example. This is a mouse brain, okay, rat's brain sample. So this is the topography, means height image. Okay, at the same time phase image is this one. Okay, it's measured at the same time because we are getting phase, amplitude and topography at the same time, because it's just one scanning only. And in different ways we are getting the same signal. We are splitting into three. Okay, one is the phase. What is the phase difference in the while it is scanning? What is the amplitude difference while it is scanning? What is the height profile we are getting? So height profile is called the topography. This is the phase image. You see same image, but the edges of the cells you can actually see stronger, and inside it is soft material. Okay, so that resolution you can get very easily. Okay, so the phase image can tell you the strength of the material or how soft and strong the material is. Okay, and that's why mostly for other samples it may not be useful, but for biological samples it will be extremely useful. Okay, this is another example. So this is a nanoparticle. This is a protein nanocomposite, nanoparticle composite. This is the height image. You don't get any information. Okay, you can actually measure the height like this, and you will see what is the height of the particle or the size of the particle. But in amplitude image already you can actually see some more structures are there. Okay, some fine structures are there. In phase image you can actually see this is a core shell structure because the core is stronger, inside is a softer material. So you can actually very clearly see. Okay, same material, same image, but different information. Okay, so non-contact mode or tapping mode can give you this information. Tapping mode is better for higher resolution. Okay, and non-contact mode is better for getting a better phase image. Okay, because once you tap it, the phase is different. Okay, because you are coming into contact. Okay, but both you can actually use. I mean, tapping mode and non-contact mode you can use for getting these three images. So this gives you height image, and in height image you can actually see a line like this. Okay, that actually shows that you are scanning a little too fast. Okay, so why it is like that? Because you see when it may be scanning from let me see. Yeah, so what happens is that if it is scanning here, the feedback says that okay, you have to go up because there is a particle. It goes up. Okay, and then what happens? If we are scanning too fast, before the feedback tells that you have to come down, we are already going far away. Okay, so it either in this way or in this way, it actually feels that it gives an assumption that there is a particle all the way. Okay, so to avoid that, you scan slowly. Okay, then the tip has enough time. The feedback will have enough time to go over it and then come back to the original position and then to scan over. Okay, always slow scan is better. Only problem with the slow scan is that if the AFM is not stable, okay, for some reason, even temperature variation because of AC can affect it. Okay, so there can be drift. So which means that you may be scanning like this, and suddenly you will scan somewhere else because there can be a drift in the sample. Okay, so if the AFM measurement is stable, always slow scan is better. Okay. Slow scan means it will tell you, I mean, how many pixels per second to, and you just vary it and see whenever you are getting a good image. Okay, all those things I hope will come in the hands-on session. It's another example. This is a polymer micelle, and you can actually see the bun-like structure. This is height image. Face image shows exactly the same thing, but with more details of how soft and hard different portions are. Okay, so not all AFMs are working in air. Okay, some AFMs are working in vacuum, ultra high vacuum. Okay, when people want to work with atomic resolution and all, it's extremely high vacuum, 10 raised to minus 10, minus 9, that kind of vacuum. Okay, space vacuum. But normally we do it in air, and biological samples can be done even in liquid. Okay, because some, for example, neurons or brain cells, or if you want live structures, okay, then you have to immerse it in liquid. Okay, so in those cases we have to modify this equation, because here the viscosity of the liquid also will be added. Okay, in that case the entire tip, this structure will be the entire, not all these things, the tip and the sample, everything will be in that liquid. Okay, it's called liquid cell AFM. Okay, now the vibration is different because I'm vibrating the tip in a liquid. So what happens? The viscosity of the liquid also comes into picture. So that's why there are some modifications here. Viscosity times comes into picture, and this is the basic force, and this is Z minus U. It's the deflection of the cantilever. Okay, so the total force, Z double dot is basically acceleration of the vibration. So mass into acceleration is the force. So this is the force due to the spring constant. This is the viscous force, and then from there we can actually again take back. This is valid even in air, because air also has a viscosity. Okay, so we have to put the viscosity of air if you are taking air. If it is vacuum, this term will be 0. Okay, so you can find out the amplitude of oscillation. This will be the original frequency you are giving in this one, but when the tip is in contact with the surface, frequency changes. That is this frequency. This is the Q factor. Q factor depends upon the viscosity of that part. Okay, all those things. So this is how we get amplitude information and phase information when the cantilever is vibrating. Okay, phase oscillation also we can get. This is arctan of again Q comes here, W and W0. So very easily we can, from the same signal of the vibration or deflection of the cantilever, we can separate out what is the frequency component, what is the phase component, what is the height component. Okay, so we get 3 images at the same time, actually 6 images. Okay, because the scanning happens like it goes from left to right, and then takes one step down, come back to left, one step down, come back to right, like that. And most of the software, they split all the left to right will be in one image, all the right to left will be in another image. Okay, and there's an advantage of doing that. For example, if I just a second, in this case, okay, I said that there is a line here. Okay, and how do I know whether that line is original or artificial? Okay, if I look at the left images and right images, I can see just opposite, because left means it is jumping over this one and going in this direction. Right means when I am coming back, there is no problem, and jumping over, and then there will be problem if the tip is if the feedback is not correct. Okay, so right and left images, if they are exactly the same, then we can say that whatever we see there are real images. Okay, did you get that point? Because you see now here, suppose the tip is coming from here, and it is jumping over this one, and the feedback, before the feedback response, I am going this direction, so it looks like the tip has a hysteresis, that there's something in it. Okay, so I drag along this side, but on the reverse scan I am coming just opposite, so there won't be any problem here, but jumping over, and that line will be on the other side. Okay, so we can actually compare and see whether there's any artifact in our imaging, okay, in the scanning or not. So left and right we can compare and see whether what we see original. Also, what can happen is that there can be a lot of noise sometimes, and the noise will look like original features, okay, like atoms or nanoparticles. So if you look at left and right, the noise will be opposite. Okay, in one, the noise if going like this, the other will be on the other side. Then we can see that, okay, this is just noise. Even the fan which is rotating can give a noise, because there's a 50 hertz oscillations are there. In STM especially 50 Hertz our current can give, it looks exactly like atoms, okay. We'll see that it will be atomic resolution. But if you look at X and Y, I mean left and right images, we'll see that the noise will be opposite, okay. Like that we can identify whether it's an artifact or not. Likewise here also, okay. So you will get basically 6 images. Here also in amplitude variation, frequency variation and phase variation gives you all these things, okay. Non-contact FM, generally the advantage is that no force is exerted on the sample. Disadvantage is that lower resolution. To overcome that we have the tapping mode, okay. So tapping mode is usually preferred over contact and non-contact AFM. Now it comes almost like an STM, okay. The conducting tip, sample doesn't have to be to conduct, okay. A sample can be insulating. We are not going to measure any current or something, but the tip has to conduct. If in Kelvin probe what we are going to measure is the work function of the material, okay. It's a very useful technique, actually more useful than STM, because STM needs the sample also to be conducting. Here even if it is if the sample is not conducting, we can get it. How do we do that? So work function is defined as Fermi level to vacuum level, okay. How do we know that? We have this photoelectric effect. Photoelectric effect means we have a metal and we shine light, and the moment we start getting electrons out of this material, we say that okay, that energy corresponds to work function. And where is that value? For example, if work function of a material, silicon is 4 electron volt, for example, okay, 4.2 actually, but 4 electron volt. What does it mean actually? It means that from vacuum level means what? If I have a crystal, okay, and I am taking an electron just outside from the crystal. So now the electron is actually confined in the crystal, which means that it is totally bound state, okay. So in physics we say all bound states are negative energies, minus energies. That's why valence band is minus 5 volt, minus 6 volt. Conduction band also is minus 3 volt, minus 4 volt, okay. All these are bound states, which means that if I take an electron from a crystal just outside the crystal and it has no kinetic energy, zero kinetic energy, that energy required to take that electron outside the crystal is the work function, okay. It's basically defined for metals, but we define the same for insulators and semiconductors also, okay. So the energy required to remove an electron outside. So outside means it has zero energy, it is not bound anymore, it is a free electron, but it doesn't have any money with it, okay. So it's a zero level, zero energy level. That's what we call vacuum level, okay. So that top line is the vacuum level. So the energy required to take an electron from Fermi level to vacuum level is defined as the work function, okay. This is what we are going to measure in the Kelvin probe, and it's a very important measurement because the work function decides whether it can be useful for a device application, okay. Because work function should be high for your sample, so that electron can flow from a metal to the sample. You might have made, for example, if you have nanoparticles, and if you make contacts with the nanoparticles, okay, you make a film of the nanoparticle, you make a contact with metal contacts, maybe silver or gold or something like that. With using silver, you will get a very good electrical current. With gold, you may not get any current. That's because of the work function difference of silver and gold. Okay, so in deciding what type of material contacts you need, this work function measurement is extremely important. Okay. So work function also depends upon the crystal orientation. If you have a polycrystalline sample, crystal orientation depending upon the orientation and whether it is amorphous and crystalline, work function will change. So suppose you have a polycrystalline sample, so every crystal will have different work functions. But if you are measuring the work function using a ultraviolet photoelectron spectroscopy, you will get an average of all these things, okay, for all these crystals. But using an AFM, we can individually every crystal work function you can measure, okay. So okay, I'll just go a little faster. Now so how it is going to measure is, now we have this tip, okay. As I told you before, the tip is now conducting tip, and we cannot just put a metal tip on a cantilever. What we do is that take the cantilever, just evaporate some gold or platinum, okay. We don't have to do that, we can buy platinum coated tips. So the tip will be coated with platinum, and suppose this is the work function of platinum, okay. So this is platinum tip and this is the sample, So you see the sample has a different work function comparing to platinum. Okay. Now if you bring two materials of different work function together, what happens is that you see the Fermi level is different. This much Fermi level difference means that there is a small voltage happening there, okay, occurring there. It's called surface voltage. Okay. So I don't know whether you remember about Schottky barrier, ohmic contact, all those things. Basically what happens is that probably you remember the diodes, PN junction diode. When we put one P and one N together, suddenly we have a structure like this, right? The band diagram we draw like this. What happens is that Fermi level is a measure of the average energy of the electrons there. It's not the average energy, but it's proportional to the average energy of the system. Okay, so this is your sample, nanoparticles or whatever it is, and this has certain electrons have certain energy. The tip has a lot of electrons in it. It has certain other energy. So what happens? It is like if you put this into contact, it is like a hot water and cold water putting together. Okay, there will be heat exchange. Likewise, there will be electron exchange until this difference is over. Okay, it will become one single Fermi level because a lot of electrons will flow. But now what happens in AFM? We don't allow this tip to touch the sample. We keep slightly away. So what happens? The difference between these two. Okay, if it is say a 0.5 electron volt difference, it is like applying 0.5 volt across it. Okay. Now because of this, I don't know whether I am clarifying it or making it more complex. Okay. So the Fermi level difference between the tip and the sample induces charge on the sample. Okay, to be very normal. Okay, because the Fermi level difference means that it is like a contact potential there. Okay, and that's why we call it contact potential difference. Contact potential difference is that if you take a tip with a certain work function, and if you just bring it close to a sample with a different work function, whatever is the difference in the work function will be like a voltage between the tip and surface. We are not applying any voltage, but it's naturally like a voltage there. So now we have a tip, we have a sample. If there is a small voltage happened in between, what will happen? Charges will accumulate, right? Like a capacitor. Now that charge we can measure. Okay. If you measure that charge, we know how much charge accumulated on the surface of the material. I think it is here. Okay. So this is a tip, this is a sample. If I bring the tip and sample close together, this has a different work function, which means that there will be some charges accumulating here, some opposite charge will be accumulating here. If electrons are accumulating here, holes will accumulate on the other side, or positive charge will accumulate on the other side. Now this gives a capacitance. Okay, it's like a capacitor. I can measure that capacitance and then measure. So this number of charges accumulating will be proportional to the Fermi level difference or the work function difference. Okay, that's why we don't directly call it work function. It is called contact potential difference. That means when the tip comes closer to it, that Fermi level difference or the work function difference creates charges. These charges will be proportional to the voltage. I mean, in capacitor also we know, right? I mean, more voltage we are applying, more charges will come across it. So these charges will be a measure of the number of measure of the Fermi level difference or work function difference of the sample. Okay, and it's very powerful. If you come closer, more charges will come because the distance reduced. So we know capacitance is given by Ka by D. The D is the thickness, the separation. So it comes closer, capacitance will increase, more charges will accumulate. Okay. So basically here what happens is that we cannot just measure charges. We don't have any equipment to measure a few charges, but we can measure current very easily. Okay. So now what happens if the tip is oscillating? It has low current, low density of charges, high density, low density, high density. If it's oscillating like this, you will get a small current outside. Okay, because of this charge, because of this oscillation. And that current, however small it is, we can actually amplify it and measure it, like an STM. And from that, we can actually calculate how many charges are accumulating here with respect to distance. How many charges will accumulate here, and that we can measure. And that measure will give you what is the contact potential difference, which is the work function difference between the tip and the sample. Okay, so from this configuration, we can measure the difference between work functions of the tip and the sample. And platinum is coated on the sample, so we know what is the work function of platinum. So very easily we can calculate the difference. Okay, so whatever is the contact potential difference we measure, we add to the platinum work function. That will be the work function of the sample. Okay. So yeah, that's all written here. So you can read it. I will send you this. Okay, if you are interested in theory, that also is there. So basically, we are driving this tip in a sinusoidal way, so that we are, when it is coming closer, more charges will be here. When it's going away, less charges will be there. So more charges, less charge. That oscillation give you a small current. Okay, potential difference we can measure, and that potential difference will be exactly the work function difference of the tip and the sample. Okay, so very easily we can measure the surface. Okay. Yeah, so then the total force will be, in that case we have the topological information, which is actually the van der Waals force, and then from this driving force we can actually measure the contact potential. Again, something called the capacitance microscopy, which actually tells you the defect levels in the material. Okay, all those charge related properties we can measure. This is from our own work actually. This is copper oxide sample. Now copper oxide is a semiconductor. Okay, sometimes it is p-type, sometimes it is n-type. So we don't know what happens. It depends upon the deposition technique. It can vary. So this is copper oxide AFM. Okay, you can see granules, and this is the height profile. Okay, something like a 10 nanometer is there, height every granule. At the same time, if you look at the contact potential image, okay, this is an image. We can actually map the contact potential, the work function over the surface. And if you are getting anything, that means there is a work function difference between here and here. Okay, so if you're getting any image in the contact potential image, that means there is a work function variation. Otherwise, you don't get any contrast, right? Everything will be plain. Now, what we did is that we shine light on that. So you see, initially the contact potential difference is large. Okay, so it's around 60 milliampere. That means the work function difference between the tip and the sample is around 60 millivolt. And then we shine light on it, suddenly it dropped. Okay, so it is dropping means the Fermi level goes up. That's why the difference is dropping. Fermi level goes up means it is n-type material. Okay, so like that we can actually identify the work function of the material, the type of the material. These are all additional. I mean, normally we don't do that in AFM, but if you have Kelvin probe attachment there, we can actually do that. Okay, and it's very powerful because suppose you are making a nanoparticle and doping it with something. Suppose a zinc oxide, doping it with something, cobalt or anything. Okay, and you don't know what is happening there. So if you go and look at this nanoparticles here, and you just shine light, if contact potential difference is increasing, you can tell that it is becoming more and more p-type. Okay, because Fermi level is going down, so work function is increasing. So when work function increasing means with respect to the tip, work function increases. Like that you can actually calculate how much photosensitivity it is, even how much work function variation is there on the surface. Okay, like that. Okay, so in light and dark you can see the work function difference, and based on that we can draw the entire band diagram of the material. Okay, just a small analysis you add up and you'll get the total band diagram. This is a tin sulfide sample. You see this is the height image. You don't see anything very clearly there. That means the work function is more or less constant on the surface, and that's better actually, because work function should not vary from here and there. Okay, this is it's a complicated material we did in collaboration. It's a self-assembled monolayers are there in this regime. You can again measure the this is height image, and this is the KPFM. That means the surface potential image. You can see the agglomeration of molecules creates more work function there, which we cannot see here. Okay, so there, I mean, work function is coming from the how molecules are staying closer and how their configuration is together. Okay, so that we can actually measure very clearly. Whatever we don't see here, we can actually see in the same image, but Kelvin probe image. Okay, and there is now for measuring the work function of material, there is something called Kelvin probe. Okay, that will measure on a large scale, not on AFM scale. On a large millimeter scale, you can measure the work function of materials. Okay, using Kelvin probe. That is not AFM. Okay, all Kelvin probes are not AFM, but this is Kelvin probe AFM. Okay, in AFM we use the Kelvin probe. Okay, and the zinc oxide samples you can actually see. This is the topography. This is the work function imaging. You can see wherever the work functions are different, like that. Okay, so zinc tin oxide samples, different zinc to tin ratio. Again, we can map what are the defect levels there. Okay, If all the nanoparticles are doped in the same way, that also we can measure, because if one nanoparticle has one work function and another, you see, if you look at here, there is not much correlation. Okay, so if this nanoparticle has a different work function than this nanoparticle, which means that the doping level is different in both. Okay, and if you are measuring using any other technique, for example this ultraviolet photoelectron spectroscopy, you will get an average of the entire sample. You don't see that there is sample to or particle variation you cannot measure there. Okay, so this is for, again, more localized measurements. So contact potential difference or work function difference you can measure very easily, and you can convert that into work function, actual work function of the material. So electronic states of the unknown material can be identified. This can be used as a controlling mechanism in ion implantation. So ion implantation is very important in CMOS technology, where we take a p-type material, silicon substrate, and we have to implant ions, implant phosphorus to see whether it has turned into n-type. Okay. There, if you measure the surface, suppose I am giving a silicon piece, and in one side, I suppose in a small area I have doped with the n-type. Okay. Suppose it's p-type silicon I am giving you, and I am doped with I have made patterns of n-type. That means implanted phosphorus in it. There is no way to identify this. But if you just do a Kelvin probe measurement, you can see that p-type and n-type Fermi levels are different. So work function will be different. So very clearly you can identify in a flat sample where is the doping happened. Okay, what type of doping, all those things. Study chemical and physical properties of clean and contaminated surface, because work function will change if the surface is contaminated. Okay. Another is conducting AFM, which you already know. It's very similar to STM, but conducting AFM has an advantage. Conducting AFM works on contact mode. STM has the problem. STM works only, it's a tunneling distance is there, so it needs to get tunnel current. But here, AFM can work in STM mode, where the tip is away from it, and tunneling current we can measure it using AFM itself. Conducting AFM itself we can measure it. But this is usually, the tip is in contact, and again it's a conducting tip. We can measure the current between the tip and the sample. And that also is very interesting, because on a surface, if you are scanning in contact mode, and if you just measure what is the current coming through, if there are grains and grain boundaries, all those things, you can clearly distinguish between the conductivity of grains, conductivity of grain boundaries, all these things. Okay, very, very useful, very, very powerful. I'll show you an example. Okay, this normally happens in tapping mode or in contact mode. Okay, if the sample is soft, tapping mode is better in this case. I will just you see, this is a solar cell material basically. This is copper zinc tin sulfide. Okay, copper zinc tin sulfoselenide. It's a long material. Okay, this is the topography. At the same time, if I look at the current image, okay, that means the conductivity image. Every pixel here is a current, but on tapping mode or in a contact mode, you can see that there are grains and grain boundaries. Grains conduct less, grain boundaries conduct more, because grain boundaries have a lot of defects. Grain boundary is like two grains coming closer. The space in between two grains is the grain boundary. And since their crystal orientation is not perfect, there will be a lot of dangling bonds, like our surface. Okay, dangling bonds will be there. So now basically we are conducting across like a STM, but in the contact mode. So if you look at that, you see the grain boundaries are more brighter, which means that the conductivity is larger there. Okay, so you can actually see how big the grains are, how good they are conducting, because this is a solar cell material, so it has to conduct. Okay, and where is the maximum current coming from? Through we know that it is from the grain boundaries here. Okay, yeah, it's another material, and here you don't see that much variation, which actually means that all the grains are equally conducting. Okay, more or less uniformly conducting. This is a work we did again. So what we did is that we grew zinc oxide nanowires, and we applied voltage across the AFM tip and the surface. So we could make actually single nanowire diodes. Okay, so with and without this is a blank nanowires. This is a nanowires with the zinc oxide arrays here. So you can actually see the new voltage shifting and all. So nanoscale devices we can make and measure the properties of that. Okay, which is very difficult in STM, because STM needs tunneling current. This is in contact mode. So whatever conducting path is there, it will conduct. Okay, it's like a contacting. This is conducting AFM. You see, as I told you, right? I mean, if you are allowing a very small current to pass through, basically the current density is very large. Okay, so it's a huge current density is there. So if you have a carbon nanotube and you just place your AFM tip, conducting AFM tip at the edge of the carbon nanotube and just apply a small voltage there, what happens is that because of such a high current density, it will strip it open. Okay, it will burn the side of the carbon nanotube. Suddenly you see that the entire carbon nanotube is opening up and it becomes a sheet of just an open sheet of graphene. Okay, so this was from one Jack's publication, not from us. Okay, so it's a graphene oxide also you can actually make. You can oxidize on the way wherever the tip is going. So basically you can do nanolithography, nano writing you can do. On graphene you can oxidize graphene, you can make it. On oxidized graphene, which is graphene oxide, you can reduce it into back to RGO, reduce it to graphene oxide. So like that you can do nano patterning using this AFM. Okay, I'm very quickly going. Magnetic force microscope is where the tip is magnetic. Everything is same. Only thing is that the tip and the configuration is changing. Okay, conducting tip which is not in contact gives you Kelvin probe. Conducting tip in contact gives you current, conducting AFM. Now instead of conducting tip, you just use a magnetic tip which has a well-defined magnetization. Okay, and then you use the surface which is magnetic. Okay, and there's a example for that. You can actually clearly see the magnetic domains in the material. This sample will look very flat and perfect. Okay, there won't be any variation. But within that sample, if there is magnetization difference, that's how we type in our pin number in our bank card, right? So we just first type in the magnetic type earlier bank cards. Okay, that pin number is now imprinted magnetically, like our magnetic type, whatever we used earlier for recording things. Magnetic types are using the same thing. Even in our laptops, right? The hard disks are still using magnetic materials. It looks flat, but magnetization will be different on the surface. And if you want to, this is exactly like a magnetic tape works. Okay, because if you just move a probe, magnetic probe through this line, you can actually see wherever it is written, information is written, wherever information is not written, everything you can clearly see. So only in magnetic AFM you can see this difference. Otherwise, all other AFM it will look flat. Okay, so there may not be these features available on, there may not be any difference in the height, but magnetization is different. Okay, yeah, so one more thing is, last one is lateral or friction force microscope. You can actually, if you have a carbon nanotube or a biological molecule on a surface, if you want to move it on the surface, okay, how much force you need. This is very important and very interesting one, because who are working in biology know about protein folding. Okay, what is protein folding? If you take an egg and egg white looks transparent, right? But when you boil the egg, it becomes a solid and it is white in color. What happens? You have longer chain of proteins, they curl up like our telephone cables, they curl up and then they become stronger, right? How much force is taken to unfold it? How can we measure it? Okay, so one protein is there. If I heat it, they curl up and they become a bundle. I just want to reopen it and see how much force it took to curl it back. Okay, what can I do is that fix one edge of the protein on the surface, another edge on the AFM tip, and slowly pull it. Okay, it's happening. Okay, it's a lot of work is already published on that one. You can actually see every time one folding is opening up, you see a jump in the force. Okay, so like that until it completely stretches out, you can see how many nano newtons of force. It's only nanonewtons or piconewtons, very small force if you take one molecule. Also another work in this case is take one strand of DNA, fix on the surface, another strand you just pull it by AFM tip. How do you pull it up? You can actually, at the end of the AFM tip, you can put a carbon nanotube. Okay, in a microscope, you can actually put a carbon nanotube at the end. Carbon nanotube has an open end with the dangling carbon bonds. You can attach an antigen there or an antibody. Okay, and then go to your antibody and then what happens is that if you measure the force, with how much force the antibody and antigen interact each other, you can measure it. Okay. So for biological field AFM, this kind of you can do force measurements and how much force, I mean basically why do we measure all these things? Because it tells you how much energy we need, okay, to do all these process in a biological process, how much energy it takes for an antigen antibody interaction. Okay, I am not a biologist, so if there is anything wrong in that side, please. Yeah, so in biology, these interactions are very, very important. Okay, so biophysics field, AFM is kind of must. Okay, so it can give a lot of information in biophysics, biology related fields. So this is this is what I was doing. What you are seeing is again graphite surface. All these small noisy bumps you are seeing, they are atoms of carbon. Okay, so when the tip is stick here, see it's called stick slip. That means if you take a chalk and draw on the board, you can make knots, right? I mean this kind of sticking and slipping. That's called stick slip. So it takes some force to start the stick slip, and then it actually goes like that. So that's why it is contact mode. It takes some force to start jumping, and once it starts jumping, it jumps over the atoms. And you can actually, if you measure this distance between these two rows, it's exactly the distance between carbon atoms in a graphite. Okay. And if you just draw on the surface like this, you will get first initially sticking and then jump over the atoms. And if you go back in the same line, you see it goes like that. So the energy or the area inside that loop is the energy dissipated while jumping over the atoms. And why do we do that? That actually tells how much energy will be released or how much energy will be wasted in a nano mechanical contact. Okay, for example, nano electromechanical systems are there. And when we published this one, now I think it's more than 200 citations already there, because accidentally biology related researchers are citing this one. Okay. So what happens is that here also we can actually see the force between atoms, the biomolecules and the receptors, all those things. Okay. Yeah, I think that's it. Summary of AFM. I don't know whether it was really useful. Maybe it's all what already you know things. But contact mode is good for very flat samples. You will get very high resolution, but not for soft samples. Non-contact mode is good for soft samples because you are not touching the samples anymore. But then the resolution will be lower than the contact mode. But intermediate is there, tapping mode, which can give you very high resolution. At the same time, no problems of contact mode, higher resolutions of the contact mode. Okay, so you can actually combine this thing. So tapping mode is safe and better. Okay, you can actually use, if you are really working on atomic resolution of materials, you can use contact mode because your sample will be very flat. Okay. On the other hand, if it's very rough, go for non-contact mode or tapping mode also is fine. Okay. So these are all additions of AFM. Okay, thank you.